Welcome back to the bench. Coda Carnus here, and today we're going to be looking at how to plug one of these things, which is a ultrasonic distance sensor to the good old Arduino. So if you've ever seen a documentary or anything about how bats work, basically this is how bats work. Sends a pulse of sound out, hits an object, comes back in, and you record the time sent between the pulse going out and the pulse coming back. So it's basically radar using sound. So we have 4 pins on this: VCC, trigger, echo, and ground. VCC obviously is voltage in. Trigger is to trigger the transmitter to send the pulse out. Echo will go high until the pulse is returned, and then ground is ground. So let's get this set up. So get some trusty wires. Those are the wrong trusty wires. So, right. So VCC to pin 5. So not pin 5 volts. In. Green for ground, from ground to ground. And then, which one's trigger? Trigger that is yellow, echo is orange. And we'll go echo to pin 9, trigger to pin 8. So what we've got is power coming in here, red and green, and then the trigger and echo pins to pin 8 and 9. So that's the easy part. Let's get some coding done. So let's start off by defining some variables. So hash define, trigger pin can be 8 and echo pin can be 9. So what do we need to do? Well, let's start off by the ubiquitous serial port so we can monitor what's happening, and we'll just start off by going serial.println, setting up pins. So trigger is an output pin because we're sending information out to the device. So trig pin, and we want to send that's an output. And then echo is a input, so we go echo pin input. Input. So this one will be sending a pin out, this one pin in. Now, how do we talk to this thing? Right, so if we go have a look at the data sheet, you can see that what we need to do is send a 10 microsecond high pulse out on the trigger pin. So let's do that then. So digital write, write, trigger pin high, delay microseconds 10, and digital write. So this is called bit bashing because you're literally just triggering the pins up and down manually rather than using a library or anything like that. And the libraries will bit bash anyway. So look back at the data sheet. We have done this 10 microsecond TTL. Then the next bit, that bit there, is done automatically by the device. It'll send out 8 quick pulses. And then what we need to count is how long the echo pin is held high. And that will be in proportion to the range to the object. And basically that's the time of flight. So how long does it take for the signal to go out, hit the object and come back? So we now need to listen for that. So how do you do that? Well, there's this nice thing called time in microseconds called pulse in. And basically what you say is, there goes, measure the length the pin is high. And you notice here it says it needs to be called before the start of the pulse. So if we do echo pin high, look at the data sheet because it's easy, you'll see that we sent the ping out, then we have the amount of time it takes to send out 8 of these bursts before this will go high here. So as long as we've started listening to the echo pin before the pulse starts here, we're okay. And given the fact we're doing it straight away, we should be pretty good. So let's just try that. So serial.print, and we'll print out time, and then we'll just print line the time in microseconds. Oh. So first off, I need to plug the module in because I haven't done that yet. There we go. Windows is saying it's there. So let's verify it first. Have I written it right? Yep. So let's upload it. And once it's finished uploading, make it a bit bigger so it's easy to see. And let's listen to the serial monitor. So hopefully, there we go. So we can see that it's returning a fairly constant. So if I then put my hand in front of it, oh, it's a lot faster. Moving my hand away, moving my hand in, moving my hand out. Right, well, that's a time of flight. So that's not so useful because how long does it take? So what we need to do is if we look back at the data sheet and scroll up a bit, in this data sheet, or is it down? Might be down. Here we go. So they've done here, so the distance, it's speed of sound in meters. So I was looking at this going, that doesn't make sense because the speed of sound is 343 meters per second. And they've in fact done the maths wrong here because 170 times 2 is not 343. It's 340.3. So let me show you the maths. It's not too complicated. So let's just move this up a bit. So what's the maths? So we have 343 meters per second. So that there is the standard speed of sound at sea level, standard atmospheric pressure, standard temperatures, all that rubbish. So what we actually want to know is how long does sound travel in 1 microsecond? Well, that's in meters per second, and we want to measure centimeters. So what we're after is centimeters per microsecond. Well, okay, so that, if you convert that to centimeters per second, is 343 and multiplied by 100. And we want it in microseconds. Well, a microsecond is 1/millionth of a second. So you divide that by a million. So you go 1, 2, 3, 4, 5. So do 0.03430. And if you count here, decimal point, what was there? 1, 2, 3, 4, 5, 6. So that's 0.034 centimeters per microsecond. So if we now plug this back into our equation here and go, well, look, we know the time in microseconds. And we go, float. Distance is time in microseconds multiplied by 0.03430. Yep. And now we change that to just a print. And then we do serial.print distance, serial.print distance. So that's in microseconds. Serial.print line centimeters. And put that there. Let's upload that. There we go. So it's now saying it's a meter. So if we put it back in the middle of the area, so it's saying, what's it, 120, 160 centimeters. So we switch back to the workbench. So it's saying I've got something that way about 1 and a bit meters. So let's find a nice hard object, because this works better with a hard object. So simple little jug. I put a jug here. And then I measure the distance. Throw my ruler at me. And that's about somewhere about 12 to 13 centimeters, roughly. So you come back to our Arduino. Hang on a minute. That's not right. That's saying it's 30 centimeters. Now, the problem is, what we're actually measuring with that 30 centimeters is the time it takes the sound to go from here to here and back. So it's actually twice the distance. What we actually need to calculate is how long it takes for it to go to there. That's the distance we're interested in. So what we're actually calculating at the moment is twice the distance, or twice the time. So let's just say this happens to be a meter. Oh, sorry, 1 second in sound time. It'll take a second for the time to hit here. Sorry, sound. Second for the sound to hit here, second to come back. When in reality, it's 1 second, but we're measuring 2. So the time we're measuring is twice what we need to. So what we want to do here is actually, this is time divided by 2.0. Oops, and it's that way. So we upload that. And what do we get? There you go. Oop, 18 centimeters, 17 centimeters. So it's not particularly accurate. I'm not sure why. So I'm just moving it around. Ah, there we go. That's why, because it was bouncing off the paper. Now I've actually got it pointing at it correctly. So this here was actually pointing down, so I think the sound was hitting here and doing something weird. It's now, bump that. But if I put that there and say, look, from there to there is somewhere between 13 to 14 centimeters, because you've got to remember the sensor is actually at the back of this aluminium can. So yeah, let's just say 13 and a bit, just under 13 and a half centimeters. And there we go. 13, if we just turn off auto scroll, there you go, 13.4, 13.45. So given the fact that the system says we're accurate to what, 0.3, I think it said. So there you go. It says the resolution at max is 0.3 centimeters. I said it's somewhere between 13 and 13 and a half, or 13 and a half and around about. So yeah, that's not too bad. So yeah, so that is how you measure the distance using one of these ultrasound devices. Right, I have the oscilloscope up and running at the moment. The yellow trace is connected to the trigger, the blue trace is connected to the echo pin, and as you can see, it's currently reasonable distance away. So the blue trace is showing a long echo return, and as I move my hand closer and closer and closer, you can see that the blue trace is getting smaller and smaller and smaller, indicating the sound waves are taking less and less time to bounce off my hand back to the sensor. And then as I move my hand away, again, you can see it gets bigger and bigger and bigger. So yeah, that's a visual demonstration of what I was saying before. The pulse time changes as the distance. So I hope you found that interesting. It's a fairly simple bit of code, but it's relatively accurate given the fact, 13 and a half seconds, 13 and a half centimeters, sorry. So I hope you found that interesting. I hope you will encourage you to use this in the future. It seems a nice little module and relatively inexpensive. So hope you found that interesting. Hope you've learned something. I definitely did when I was playing around with it initially. So like and subscribe, and I'll see you next time. Bye.